Okay? We don't multiply these two together because there's a subtraction sign in between. So all it wants us to do is to take this polynomial and subtract this entire polynomial, which means we need to subtract each term individually. So I would just always distribute and then combine like terms. Some people skip this distribution step, but I'm going to write it down just to be clear. The first set of parentheses really had no purpose other than for organizational, so it's visually appealing and organized for you. But really nothing's being distributed to that first set of parentheses. But to the second, when you are subtracting every term in that set of parentheses, it essentially flips all the signs, because subtracting a negative makes plus 7x cubed, subtracting a positive makes minus 2x squared, subtracting a negative plus 5x, and subtracting a positive minus 9. So it essentially flips all those signs. And then we combine like terms. So 13x cubes and 7x cubes is 20x cubes. Negative 9x squared, negative 2x squared makes negative 11x squared. And negative 7x plus 5x, negative 2x. And positive 1 minus 9, negative 8. Okay? But because we like polynomials so much, people get excited and start distributing 13 times negative 7, 13x cubed times negative 7, and they start going through that whole process, and that's like torture. Okay? And given that you can't use a calculator, here's how not being able to have a calculator might help you, because, you know, not that 13 times negative 7 is not doable, it's just, that's a little bit much for not having a calculator and having to go through all that. Okay? On number 2, let's see. Where's my little seating chart? What would you do for number 2, Zach?
I read second and set with the plus 3y.
Very good. Okay, we have 25x squared. Did we talk about this the other day, kind of using that shortcut? Or no? Was that my Algebra 2 classes? Okay, when you're multiplying, and I'll do this one out, but when you're foiling, obviously you get 25x squared. Your outer is plus 15xy. Your inner is another plus 15xy. And your last term obviously is 9y squared. What you're always going to get when you're foiling something times itself, aka you're squaring a binomial, is that middle term. You're always going to get two of the same thing. So essentially they end up being, you know, it ends up being doubled. 15xy gives us 30xy. And I really would encourage you to get to a point where you can take from here and get to this step without having to do the work in between. Okay, because this first term squared gives you the 25x squared. The last term squared gives you the 9y squared. And if, even though you might envision this, it can save you a lot of time not having to write it down and go through the foiling, because your outer times your inner is always going to be this term times this term, 15xy, and you're always going to have two of those, so that essentially gets doubled. If you can do that without having to expand it, it's just going to save you a lot of time, help you be a little more fluent in situations where the problem is much greater than just squaring that set of parentheses. Okay? For example, if I give you 2x plus 3 squared, I want you just to be able to say 4x squared, envision the 6x doubled, which is 12x, and then plus 9. And get that without the expansion. Okay? Just for fluency purposes. Okay? When you take a look at number 3, what does your gut tell you on that one? Lily J. So 3x times 3x, 3x times 2, 3x times negative 5y, then move on to the 2, 2 times 3x, 2 times 2, 2 times negative 5y, and then move on to the 5y. Okay? That is one way. Does anybody see anything else that could save us time? Liz?
Positive and negative 5y would equal, like when you multiply stuff.
Yes. I'm thinking of a word that we actually used yesterday. Taylor? Conjugate. If you can recognize that these are conjugates, remember the beauty of multiplying conjugates is that your outer and your inner are going to cancel, right? So if you kind of put a second set of parentheses in there around the 3x plus 2. The first piece of this product is 3x plus 2 plus 5y, and then we have 3x plus 2 minus 5y. So if we actually treat it like a foiling process, our first term is going to be 3x plus 2 times 3x plus 2, which hopefully we just kind of worked on the shortcut for that. That's going to be 9x squared. The outer and the inner is going to be 6x, so double that is 12x. And then 2 times 2 is 4. There's 3x plus 2 times 3x plus 2. Now your outer, the 3x plus 2 times the negative 5y, and your inner, the 3x plus 2 times your positive 5y, are going to cancel, which saves you a lot of time. And then your last positive 5y times negative 5y, negative 25y squared. And then you're really done. Right? This set of parentheses isn't really doing much, and there's nothing to combine. That set of parentheses was just really for visual purposes. So if you wanted to keep it, you could. Okay? So just a different way of looking at it, and actually when you did this last year in Algebra 2, that's kind of part of what the Common Core was trying to shed light on, is different ways to look at problems like this to save you time. If you did go through the way that Liz suggested, it would be the same answer. It would just take you a little bit longer to get there. Okay, a little bit crazier with the distributing and the combining of like terms. Also, actually, while I'm here, I'm going to take this just for the moment and write it like this, just to point out the difference of two perfect squares. Yes? And the difference of two perfect squares factors backwards into conjugates. Yes? Okay, so you'd have 3x plus 2 plus 5y, 3x plus 2 minus 5y, which is what we had. Okay, so not that, that's definitely not our final answer, but I just wanted to point that out. Because you're familiar with the difference of perfect squares pattern. Okay? Below here, so here we are multiplying conjugates. So the rule here when you're multiplying by conjugates is that it just becomes the difference of perfect squares. Okay? Even when we were multiplying by the conjugate last night to rationalize, it became the difference of perfect squares. In the squaring of a binomial with addition, again, it's a squared. And then you kind of envision your outer and your inner will be an a times b, so just ab. But you'll have two of those. And then plus b squared is your last term. If it's subtraction, pretty much the same thing. It's just that your outer times your inner product will be a negative ab with another negative ab, which is negative 2ab. Now, let's think here. When you cube something, okay, I don't even know if I want to do this one. Well, we'll do it, just to prove that there is sort of a shortcut there, but it's still a long answer no matter which way you look at it, so it's probably more work to memorize what I'm about to show you than it is just to cube something out every time. But when we do cube something out, we do want to expand. And do a plus b times a plus b squared. Yes? This we kind of have our shortcut for, so I'll keep the original a plus b, but then the a plus b squared, I'll use what we have up above here. And then we will distribute the binomial times the trinomial. So a times a squared, a times 2ab, a times b squared. And we move on to the b. So when I multiply b times a squared, I'm going to kind of line it up underneath this one because it's going to be a like term to that, right? A b with an a squared. So plus a squared b. This one is going to be 2ab squared, so it's going to be a like term to this one. And then b times b squared is b cubed. So when I add all that up, I get a cubed plus 3a squared b plus 3ab squared plus b cubed. And then how's the subtraction going to be different? Any ideas? Or should we just do it out? Do it out. Yeah, I don't think I'd be comfortable guessing from here. So again, I'll make this happen. Oops, just lost my lid. And then distribute your A. And distribute your negative b, which will be minus ba squared, which I'm just going to write the a squared first, so it kind of matches. Then we have a plus 2ab squared, and then a minus b cubed. So that's going to be a cubed minus 3 of these plus 3 of these and then minus a b cubed. Probably, that's definitely not what I would have guessed. But you kind of want to do that out to see the light there. Again, don't memorize those. Okay, you're going to make, it's going to be much easier for you to mismemorize them and get it wrong for that reason than just doing the skill out. They're both kind of equally as difficult, so I say just cube things out manually. Okie doke. Here's an application problem. So this is supposed to be the shaded region. So shade in between these two rectangles. And we want to write a polynomial in standard form to represent the area of the shaded region. Okay, so how are we going to calculate the area of a shaded region that kind of looks like this? Kendall, any idea? Good. A little bit of geometry. So the area of the big minus the area of the small. So what is the expression that we would start out with for the area of the big, Nathan Z? Say it one more time. Good. X plus 4 times x plus 3. That's just your length times your width of the big rectangle. And then we want to subtract the area of the small, which is what, Michelle? Good. Okay. Now, what algebra work are we going to do first here, Josh? Okay, so tell me what to write. Okay, can you keep going? Okay, what are these going to be? Say it again. Okay, so keep your parentheses around that too, because we haven't done the subtraction yet. The intention is for us to subtract the entire product, so we have to subtract every term here. Good. So x squared minus x squared cancels. 7x minus 3x becomes 4x, and 12 minus 2 is 10. Nice job, Josh. Okay. Are we okay with standard form, a polynomial in standard form? That means from the highest, like if you had multiple terms from the highest exponent down to the lowest, that is standard form. Okay, flip it over. Why don't we do this? We'll talk about these two and then we'll go back and do those on our own. The degree of a monomial. So if I have something like this, what's the degree of this? 2. How about this? What's the degree of that monomial? What? No. Nine. That has a degree of 9. Okay? So I think what we're confusing that with is in a polynomial situation, if we ever had 3x to the 5th minus y to the 4th, when it's a polynomial, you take the largest degree of any individual monomial. So this polynomial has a degree of 5. But if it's a monomial, you add up your exponents within that monomial. Okay? What about this? 2x to the 8th y z squared. 11, very good. 8, 9, 10, and then the 11th comes from the y. Okay? If we have a crazy 5x squared y to the 4th minus 2x to the 7th y plus 8x to the 6th. What's the degree of the polynomial? You have to first evaluate the degree of each monomial and take the largest. So this monomial has a degree of 6, this one has a degree of 8, and this one has a degree of 6. So the overall degree of the polynomial is the largest of those that we just listed, 8. Good, Jack. Okie doke. All right. What I want you to do is take a few minutes to do these 4 on your own. Oops, messed that up. That is x squared y.
Those cancel. Conjugates, outer, inner cancel. These are conjugates. Outer, inner cancel. Conjugates mixed. Outer, inner cancel. Minus 21, double, yes, 42.
I think on that last one, you're getting a calculator. I wouldn't want you to waste your time doing those calculations by hand.
Eight times negative 80. Let's try my square on that one.
Okay, raise your hand if you can tell me what you got for the first one. Jalen? Does anyone get anything different than x cubed plus y cubed for number 1? We all got that? Okay, good. Then I don't need to comment on it. How about for the second one? Jack? 16x to the fourth minus 625. Did anybody get anything different than that? Correct. How about on the third one? Let me go with Winter.
64y squared plus 9x squared minus 42x plus 49.
Did anybody get anything different than that? Good. Thank you for not being shy about it. Leah, what did you get? You're not, okay. Did anybody get anything different though? We'll start with trying to find the other answers first. Lily?
64y squared plus 9x squared plus 42y.
Plus 42 what?
Or x.
Good,
X.
good. Yes, so, Winter, I'll have you kind of look at your own. So when I did this, I looked at this as conjugates. 8y plus this binomial, 8y minus the same binomial. So rather than going through a 3 by 3 multiplication, which can get ugly, I did the conjugate method that we kind of talked about before. So your first times your first is 64y squared, right? Because they're conjugates, your outer and your inner will cancel, and then your last times your last will be a negative 7 minus 3x squared. But I actually have to square that out. So that's what I did next, is I squared out the 7 minus 3x using my little shortcut there. 7 times 7 is 49. 7 times negative 3 is negative 21x. We double that, negative 42x. And negative 3x times negative 3x is 9x squared. And then distribute your negative sign, and then rewrite in standard form. So I would kind of flip the 9x squared around just like I think, Lily, you said, right? Did you put the y squared first or the x squared first? Yeah, it doesn't really matter, but so she said 64y squared plus 9x squared plus 42x minus 49. Okay? Yes, Jalen? Oh, you're right. So it's a positive 9x squared, and then we distribute that. Did you say positive 9x squared, Lily? I think you did too. Did you make that same mistake? Yeah, so it isn't good catch. So minus 9x squared. I think that's worthy of another bonus point. Oh, and you already had your one today. Look at that. And lastly, there's your 8x minus 5 cubed. This one, because you end up doing like 64 times 8, I felt like we needed a calculator for that one. Okay? Homework's there at the bottom.
I don't have textbook open. I'm going to be reading the whole thing just to hand in, say, before I get out of there.
You're going to redo the whole thing?
Yes, because my thumb was killing me.
Okay.
I feel the rash in my face.
Okay.
And
If
plus, I
you-
took extra time. I do a study all today.
Well, if you did already do it at home,
Yeah, I know it's at home, but
I'll take it to